Now next, there are some problems that you cannot do with Newton's laws because there's a changing force. If the force is changing, you could use calculus and Newton's laws, but it turns out that even without calculus, you can use conservation of energy, and it ends up being a lot easier. Let's take an example right now. So here's the situation. My question is, how much higher will a 5 kilogram mass get if placed on an unstretched spring right here of spring constant K is 2 newtons per meter, and then shot upward with V initial equals 3 meters per second. So how much higher is this going to get upwards? So the only way to solve this actually is using energy conservation. Let's identify what our system is. Our system consists of the mass and the spring. Here's our whole system right there. Truly, gravitational potential energy does include the Earth too, because without the Earth, we would not have any gravitational potential energy. Any change of the Earth's motion would be negligible. So now we got to figure out our initial and final positions. Well, I've drawn both the initial and final positions here. So it starts right here, and at this level here, and it ends up at this level here. So now we got to figure out where to call zero, where to call our energies of zero. Well, we've got actually two different kinds of potential energy. We're going to have spring potential energy and gravitational potential energy. So this is the unstretched position. So I'm going to identify that position right there as US equals 0. And we kind of have to do that, setting the unstretched position as the spring potential energy 0. Otherwise, you get into these crazy negative potential energies and it can get very confusing. Where to set gravitational potential energy as 0? Now you might say, well, why don't we set it here on the ground as 0? Problem is, we actually don't even know how high off the ground this thing's starting. So we can't do that. So what we want to do is figure out somewhere else to set it equal to 0. Often you want to set it at the place where it starts or the place where the object ends as the 0 point. And I'm going to do that in this case. I do personally like to set lower points as 0 because a lot of times people can drop negative signs. So I'm going to actually set UG equal to 0 at this height as well for this mass. So that makes things nice and simple. This level right here is 0. So it's going to go upward to this point up here. So this is going to be a distance that I'm going to have to identify. I'm going to just call that, for lack of a better variable, h. And that makes sense because we're going to start here at 0 and it's going to get up to a height h. Cool. Now let's go ahead and write our equation for energy conservation. E initial plus work non-conservative equals E final. Now, if we look at this situation, we see that we've got a force due to a spring, we've got a force due to gravity. None of these forces are non-conservative. So this makes it nice and easy. We get to get rid of this non-conservative work. There is none. So all the forces we have are conservative forces. Mechanical energy will be conserved. So let's get more specific about the initial energy. What forms of energy does this block have initially? Well, does it have any spring potential energy? Well, it starts as an unstretched spring, so spring potential energy initial, that's gone. It's 0. We have none. How about gravitational potential energy? Well, you might say, oh, it's above the ground, so it must. But do you see that we've also set gravitational potential energy as 0 right here? So we've got no initial gravitational potential energy either. And you'll notice I don't have subscripts for different objects because I only have one object, one mass, and one spring, so I can identify those just by what objects they are. Don't have to indicate other subscripts like 1 or 2. Now, what is next? Got no initial energy. Well, wait. There is some initial energy. What initial energy form is there? Well, I am given that it has initial kinetic energy. So we've got K initial. And that's due to it's got some initial speed that's non-zero over here. Now, the question is, how much higher will it get? What does that mean about the final energy? How much higher will it get? Well, it will stop getting any higher when the velocity is 0. So that means my K final is gonna be 0. That's gonna be gone. In fact, the only, there's gonna have more than one form of potential energy, but it will only have potential energy. So it's gonna have what forms? It'll have UG final because it's gonna be higher up than 0, and it's gonna have spring potential energy final. So there is my the next step of my master equation. So let's go ahead and keep going with this and see where it takes us. Okay, so let's get more specific. These are gone. Kinetic energy initial is going to be 1/2 mv initial squared. Don't forget to square that. That's all there is for the initial energy, just the kinetic energy. When I'm all done, it's going to have gravitational potential energy. Now I've identified this change in height as h, and this is 0. So that means that the gravitational potential energy will simply be mgh when we're all done. That's the final potential energy because it'll be way up here. Okay, how about U spring final? Well, that'll be 1/2. Now I'm just going to put in the equation here, 1/2 kx squared. But what is k? What is x rather? What is the distance the spring is stretched? Do you see that all that is just h? So I'm going to rewrite it one more time. 1/2 mv initial squared equals mgh plus 1/2 kh squared. Aha, there's only one unknown in there, and that is the final height h. So let's go ahead and solve for h. And notice that I am trying to solve this completely symbolically before I put in any numbers. So how are we going to solve this? Well, as you can probably see, we've got h squared, we've got h, so we're going to have to use the quadratic formula. Just a quick review, what is the quadratic formula? Negative b plus or minus the square root of b squared minus 4ac all over 2a. And let's see if we can identify, well, we got to put this into a slightly different form. We're going to have to rewrite this as 1/2 kh squared plus mgh, and I'm going to subtract 1/2 mv squared from both sides, minus 1/2 mv initial squared is equal to 0. So as we can probably see now, the a is 1/2 k, and that's equal to 1/2 of 2, which is just 1. B is equal to mg, and that is equal to the mass 5 times g, we're going to use 10, so that is 50. C is equal to negative 1/2 mv squared, which is equal to 1/2 times m, 2.5. V initial squared is 9, so that gives us 22.5, and it is negative. So when we plug all this in, we get negative b, which is negative 50, plus or minus the square root of b squared, which is 50 squared, minus 4ac, that's 4 times 1 times negative 22.5, and this whole thing is all over 2 times a, which is just 2 times 1. Make sure, although it doesn't matter here, whenever you divide by something, make sure that this whole thing's in parentheses on your calculator. When you do this, you find that we get negative 50 plus or minus the expression under the radical comes out to 50.9, and this is all over 2. So is it going to be the plus or the minus? Now there actually is a physical explanation for each solution. In other words, physics doesn't lie. The math actually has to represent something meaningful. So let's get the answer that we want, and let's discuss what the other solution could possibly mean. So as we can see, 50 plus or minus 50.9, well, our height, if we look at our picture, is going to have to be positive. So we want the positive solution, which means we're going to use plus here. That's the one we want. So that'll be 0.9 over 2, and that gives us 0.45 meters is our final height. So this is our solution that we seek, but we could also get a value of about negative 51 meters. How is that possible? Well, in fact, notice that our V here is squared. When we use energy, we do lose information about the direction. Because V squared, if it were negative or positive, it would come out to the same thing. So what's happening here is that is the solution if it were going downward at 3 meters per second and both gravity and the spring force were pulling down. Actually, strike that. If we're going down at 3 meters per second, gravity's pulling down, the spring would be trying to compress it up but the K value is so low, that initial velocity down and the gravity also pulling down would combine, so this would squeeze a whole lot.